The James Webb Space Telescope has proven to be useful not only for the study of nearby celestial phenomena, but also for discovering the mysteries of the distant past. As we tune our telescopes to observe the birth of galaxies, an unexpected revelation shakes up our understanding of the cosmos. Contrary to the long-standing belief in the Big Bang Theory, the telescope visualizes galaxies that existed in the Dark Ages, challenging the accepted narrative. The Big Bang has been the dominant explanation for the creation of the universe for generations, supported by many studies and countless scientists. However, the James Webb Telescope, equipped with advanced technology, has identified 6 galaxies that exceed expectations. These galaxies, which exist 500 million years after the Big Bang, are up to 10 times the size of our Milky Way, dramatically changing our cosmological understanding. This announcement prompts a reevaluation of the Big Bang Theory, which is considered the absolute truth of the origin of the universe. Images taken by the James Webb Telescope show galaxies deviating from predicted size, structure, and age, prompting scientists to rethink the fundamental principles of how the universe was born. Unexpected discoveries challenge fundamental aspects of the Big Bang Theory. According to theory, galaxies should be larger as the universe expands, but the observed galaxies appear smaller than expected. The smoothness of these galaxies contradicts the expected irregularities predicted by theory and casts doubt on the dynamics of their formation. Furthermore, the observed galaxy ages challenge the predicted timescale of galaxy evolution within the Big Bang. The abundance of galaxies captured by the James Webb Telescope exceeds expectations and calls into question the accuracy of predictions of the Big Bang hypothesis. The hypothesis suggests that in the early universe, all matter and energy was compressed into an extremely small, dense point known as a singularity. But the images of the telescope show a difference in the distribution and density of galaxies, casting doubt on the basis of that long-standing theory. The Big Bang Theory, once considered an indisputable truth, is examined in the light of the pioneering observations of the James Webb Telescope. As scientists grapple with unexpected data, the ancient story of the origins of the universe may undergo a profound shift that forces us to rethink and transform our understanding of the cosmos. The images from the telescope not only capture the beauty of new galaxies, but also set in motion a scientific revolution that challenges the fabric of our cosmic knowledge. The general structure of the universe shows the tendency of galaxies to group together in large groups, forming clusters and superclusters. These complex networks encompass the entire cosmos and are compatible with the predictions of the Big Bang Theory. According to the theory, the universe was born in a dense, hot state that expands and cools over time. Because gravity played a central role in the distribution of matter, galaxies formed in specific regions, forming complex filaments connecting them. This cosmic web-like pattern, observed on a large scale, strongly supports the fundamental principles of the Big Bang Theory. Contrary to our previous understanding, observations from the James Webb Space Telescope challenge the expected evolution of galaxies. According to Big Bang theorists, small galaxies should evolve into larger ones through collisions and mergers. However, the telescope images mainly show smooth disks and well-organized spirals, which casts doubt on the general occurrence of galaxy mergers in their evolutionary process. This unexpected discovery challenges the idea that small galaxies grow significantly through mergers, suggesting that these galaxies may not have been small to begin with. A study of the size of galaxies discovered by the James Webb Space Telescope shows a departure from previous assumptions. Contrary to expectations, the images from the telescope show that the optical illusion, where objects appear smaller as the distance increases due to the expanding universe, is not observed. It challenges long-held beliefs and questions the accuracy of our perceptions. In addition, the age and abundance of galaxies revealed by the telescope cast doubt on the validity of the Big Bang Theory. Equipped with infrared filters, the James Webb Space Telescope takes images that help estimate the age of stars and galaxies. The stellar populations of some galaxies are over 1 billion years old, contradicting the theory's prediction that they should not have existed before the Big Bang. This challenges a key assumption of the theory and suggests that the Big Bang may not have been the only event that started it all. The telescope's observations also contradict expectations of a decline in the number of observed galaxies over time. Rather than introducing cosmic darkness, as some Big Bang theorists predict, recent studies show a remarkable abundance of galaxies, challenging the theory in a relatively short period of time. Despite significant inconsistencies and challenges to the Big Bang hypothesis, its potential collapse has not been widely acknowledged in the mainstream media. The lack of attention may be due to several factors, including the deeply embedded nature of the Big Bang story in popular scientific discourse and the broader cultural understanding of the origin of the universe. Scientists who dare to challenge the traditional Big Bang theory face enormous obstacles in obtaining funding for their research projects. The dominance of the Big Bang story in the scientific community and in the public imagination has created an atmosphere where different viewpoints meet with skepticism and opposition. The established narrative is so entrenched in the scientific community that questioning it is often met with reluctance and hesitation. In addition, prevailing theories strongly influence the distribution of research funds, and the Big Bang theory, the cornerstone of cosmology, receives considerable support. Therefore, it is difficult for researchers who propose alternative ideas or criticize the existing theory to obtain the necessary financial support for their studies. The reluctance to accept possible errors in the Big Bang theory can also continue simply because of the disruption of the scientific status quo. Scientists who openly challenge theory risk being labeled as unorthodox or even controversial, making it difficult for them to be recognized and supported in the scientific community. In essence, the lack of widespread awareness of the potential collapse of the Big Bang hypothesis in the mainstream media is a complex interplay of scientific conservatism, institutional inertia, and the significant influence of established narratives on science funding and public perception. A reluctance to address the inherent shortcomings of the dominant scientific framework, along with censorship, hinders progress in cosmological research. The Big Bang theory is increasingly considered, but alternative theories such as the steady-state theory and eternal inflation offer different perspectives on the nature and origin of the universe.
Constant theory proposes an eternal and unchanging universe where constant creation maintains a uniform density of matter. On the other hand, the theory of eternal inflation suggests that our universe is part of a larger multiverse, where each bubble universe has unique characteristics. In light of these challenges and alternative theories, the scientific community faces a critical turning point that challenges long-held beliefs and paves the way for a reassessment of our understanding of the cosmos. Introducing the theory of cosmic inflation, which explains how our universe was born from a tiny seed of strange, self-replicating matter. The concept of eternal inflation provides a reasonable explanation for the existence of multiple universes and the different properties observed in our universe. The combination of these two ideas is the cyclical model of the universe, which proposes a model in which the universe undergoes repeated cycles. Each cycle begins with the Big Bang, an enormous explosion that marks the birth of a new universe, and ends with the Big Bang, a spectacular collapse in which the universe shrinks back into a very dense and hot state. According to this model, the universe undergoes an expansion phase after the Big Bang. During this expansion, galaxies, stars, and other cosmic structures are formed, gradually making the universe larger and less dense. However, the gravitational expansion of the matter and energy of the universe eventually slows down and reverses direction. As the expansion slows, the universe enters a contraction phase known as the Big Bang. During this phase of contraction, the universe undergoes significant changes, becoming progressively more compressed and denser with each passing moment. This continuous process culminates in an extremely compact state where all the matter and energy of the cosmos is concentrated into a single point characterized by infinite density and temperature. This singularity represents the deep convergence of cosmic elements to an unimaginably small and powerful focus. After the climax of this contraction phase, the decisive moment known as the Big Crunch, the universe begins a new cosmic journey. It marks the beginning of a new cycle with another huge event, the Big Bang. This explosive phenomenon marks the birth of a new universe, continuing an eternal cycle characterized by phases of expansion, contraction, and rebirth. Central to this cyclical model is the belief that each successive cycle mirrors the previous ones. That mirror extends to the fundamental physical laws and properties that govern the universe. Periodic recurrence facilitates the repetition of cosmic evolution, leading to the birth of galaxies, stars, and many other celestial structures. This continuous cosmic rhythm, defined by the interplay of expansion and contraction, acts as the driving force behind the continuous creation and evolution of the vast cosmic tapestry we perceive. In essence, it paints a picture of a dynamic and ever-renewing universe, where the echoes of each cycle resonate with the patterns and qualities of the past, continuing the eternal dance of cosmic birth and renewal. With this in mind, the detection of new galaxies can be explained as part of a new cycle that we happen to observe. This perspective raises interesting questions about the traditional Big Bang theory. Could the ongoing cycles be the evidence needed to challenge or even refute the traditional understanding of the origin of the universe? This is a thought-provoking possibility that challenges our current understanding of cosmic evolution.